Hello and welcome to the Desco Europe ESD Basics PowerPoint presentation. My name is Tim.Hacker. I am the European Sales Manager for Desco Europe. And during this PowerPoint presentation, we will break for virtual demonstrations of some of the products that we've got here as well. So we're going to have a break to see charge generation, why we need to have personal grounding, and we'll also be looking at packaging as well during this presentation session. A little bit about Desco Europe. We are the European brand of Desco Industries Incorporated. We're based in Letchworth, Garden City in Hertfordshire in the UK. We have another office down in Crowborough in East Sussex. And we manufacture the products that you're going to see today in the US, and some are also manufactured in the UK. What we like to do is just go through the PowerPoint presentation to begin with, and then, as I say, we will break for demonstrations. And I will share contact details at the end, so you can get in contact with me if you do have any questions regarding this, or if you'd like to know anything more about Desco Europe and the services that we can provide. So to begin with, in terms of ESD basics, we're going to be looking at a couple of things to begin with, and the reason why we do this ESD control training. And the reason why is because there needs to be a training plan as per the European standard, which is IEC or EN 61340-5-1. And that training needs to be recurrent. So it needs to keep that personnel's understanding of why wrist straps are worn or why foot grounders are worn, what ionizers are used. So our operators understand the need for these control products and why they are used inside the ESD protected area. All of the training needs to be provided to personnel who handle or come into contact with any ESD sensitive devices. And initial training needs to be carried out before an operator starts down on the shop floor. As I say, it needs to be recurrent, and it's up to the company. It's user defined in the standards how often this training is repeated, how often this training is recorded. And you need to make a note to make sure that everyone has had the training. There are a number of ways that training can happen. You can watch a video like this one with a PowerPoint. An ESD coordinator can give your training if you want to do it internally. They can provide the training. The third one is having someone external come on site, carry out the training. Again, it will probably be a mixture of PowerPoints and demonstrations as well. All of these are recognized by the European standard 61340-5-1. Some of you may be working towards ANSI ESD S20-20. That one is the American standard. They are pretty much the same. There are a couple of differences. We won't go into those today, but if you're working towards ANSI ESD S20-20 or the IEC 61340-5-1, they both say operators need training. Safety. When working around high voltage, as important as ESD control is for people, it's secondary importance compared to employee safety. If anyone's working with voltages over 250 VAC, then please do not ground any personnel through wrist straps, footwear, their garments. Ionizers can be used. We've seen that used in some areas because, again, they're not making contact with an operator. But anything that the operator is connected to and they're connected to ground, do not use anything when high voltage is being used. All companies should have an ESD control plan, and that ESD control plan should be in accordance to either IEC 61340-5-1. Again, you're going to see that number a few times, or ANSI ESDS 20.20. This is what IEC 61340-5-1 says about the control plan, and that's where training, compliance verification, product qualification, all of these items come in to work together to make sure that you've got a good ESD control program plan in place. Each company should have an ESD control plan. Part of that ESD control plan is ESD training, which is why we do this training session. But if you don't have an ESD control plan, again, I will provide contact details at the end of this webinar or this PowerPoint, and you'll be able to get in contact with me, and I'll help you write an ESD control plan. So what is static electricity or electrostatic charge? And this is defined as electric charge at rest. All materials tri-body charge, and tri-body charging is when two materials make contact and then separate from each other. Some electrons are given to one surface, which causes an imbalance. Electrons are negative, protons are positive. So just walking across the floor, you can see the person's shoe there at the bottom positively charged, the floor is negatively charged, and the tape there, one side is positively charged, the other is negatively charged. And both of these charges or polarity charges need to be controlled in your ESD control program. And both positive and negative charges can discharge and damage electronic components. What we're going to be using soon is a static field meter, and that can measure the charge of a field, and after contact and separation show that one item will be negatively charged and the other item will be positively charged. So if an item is negatively charged, they will have more electrons because electrons are negative. If an item is positively charged, they would have lost some electrons, gain more protons, which protons are positive. And there are multiple events that are happening every day. As we say, tri-body charging when surfaces make contact and then separate. But a lot of things that are happening every single day is causing electrostatic charge generation, like ESD events. That could be opening a plastic bag, combing your hair, sliding across the car seat. And really, it's when the charge is greater when the weather is cold and dry. So humidity plays a factor in this as well. And that discharge is when that charge moves. Okay, so remember that some people think that static electricity as being at rest or not moving is actually causes the most concern when it ceases to be stationary. So when it starts moving, that's when it's of most concern, and that's when items can charge up and damage ESD sensitive devices inside the ESD protected area. So just a little recap over the last couple of slides. It's when two materials make contact and then separate. As electrons transfer, the deficiency or surplus of electrons creates an electrical field, which is known as static electricity. And the simple separation of two materials, as when we saw a second ago, tape is pulled off a roll, that can transfer or create a transfer of electrons between surfaces, generating those electrostatic fields. The amount of static electricity generated depends on the materials, the friction, the area of contact and separation, and relative humidity. So remember, at lower relative humidity, the environment is drier and charge generation will increase significantly. Common plastics generally will create the greatest static charges, which is why plastics are not allowed within 12 inches or 30 centimeters of a board or some sensitive components, because that charge can jump. And again, I will show you that shortly. So this electrostatic discharge, there's a hand there that's positively charged. It's going to go and touch a doorknob there that is negatively charged. And that's because those charges seek balance. That's why that ESD event happens, or electrostatic discharge happens. That discharge is very quick, and it creates heat and energy. So if two items are at different electrostatic charge levels, as they approach one another, they do not need to touch, just approach one another. A spark or electrostatic discharge can occur. And because it creates heat, and there's that transfer of energy, it can melt electronic components, and it can damage electronic components, which is why inside the ESD protected area, it is very important that we make sure we control this. And by controlling this, we make sure that operators are grounded and plastics are removed from the area or taken away from anywhere that items are or can be damaged, or any sensitive items. And now there's just a couple of examples of electrostatic discharge. As I say, there are innumerable ESD events occurring all the time in a normal environment, so even in your home. And so most of these you do not see, you do not feel. And for us to feel it, it's about 2,000 to 3,000 volts for a human or person to feel the discharge. But there are larger ESD events that are occurring, and one of those is lightning. Lightning is an ESD event, and if you're hit by lightning, it's going to hurt, but it's also going to burn the person or the item that it hits. So if it hits a tree, you'll see that the tree will burn. Hopefully, no one is ever hit by lightning, but if anyone is hit by lightning, that's what's going to happen. It's the same thing that happens with the zap from a door, but that charge is not on the same level as lightning, but there is going to be that transfer of heat and energy, which causes that burn. And in an electronics manufacturing environment, that's when it will damage components and melt a hole or burn a hole into the component. And we can see that here. So this isn't a computer simulation. This is a technician that was connected to a small magneto. And you can actually see the charge there leaving the technician's finger, going onto the component. And what happens is it burns a hole in the component. So this is a scanning electron micrograph image of the damage after the removal of the capacitor metallization. Now, if you have a look at that, that is 10,500 times magnification. Any items that could be damaged by an ESD event in a facility, they may not have the means to magnify an image to 10,500 times. So we do call ESD events or ESD damage. It's the hidden enemy is what we call. We need to make sure that we're controlling this, and the way that we control this is understanding the different types of materials inside an ESD protected area. One of these materials are conductors. Now, these materials easily transfer electrons or a charge between atoms, and they are called conductors. Are said to have free electrons. So some examples of conductors are metals, carbon, people, because of the impurities in the human body sweat layer. So that's how wrist straps work. And some people may fail testing their shoes first thing in the morning, and then test later on in the day and they pass. And it's just that build-up of sweat in that shoe that turns that fail into a pass. So making sure that operators have their own wristbands, visitors have disposable heel grounders, because again, it's using sweat. So just to make sure everything's clean, these wrist straps as well, the people using, or if you are using foot grounders, they do need to be clean. They can be washed in most cases. So it's just making sure that you're using the right equipment inside your area. Now, I'm normally asked about dissipative materials. Dissipative materials are also conductors, but they take the charge away much slower because of the higher resistance dissipative materials. It's in the higher portion of the conductive range, and a way to explain this is matting. If you're using bench or work surface matting in your ESD protected area, the top surface could be a green or a blue color. There are other colors available, but they're the most common colors that we see. If you lift up that blue layer and fold the mat over, you'll see underneath there's a black layer. That black layer is conductive. The blue or green layer on top, that's dissipative. Okay, so that dissipative layer is going to take that charge away. And the other types of materials are insulators. So this is when electrical current does not flow easily. They cannot be grounded. So examples of these are plastics, which we'll see in a second, dry air, which is why at lower humidity we get more ESD events. But it is worth remembering, and it's a question I get all the time, is plastics will charge up as well as conductive materials. Okay, so both will charge up in inside the ESD protected area. But because a conductor is when a conductor is charged, there's the ability to transfer electrons, gives it the ability to be grounded. Okay, insulators, there's this plastic cup here that's positively charged on the matting that's negatively charged, will hold the charge and cannot be grounded and conduct the charge away. So what I'm going to do is I'm going to go onto the camera, and what you'll be able to see is a little setup here with a static field meter and a couple of panels that we're going to use to charge up. So just here is my static field meter. I'm just going to turn this on here. And it's showing there's a little bit of voltage in the atmosphere. It's actually showing minus or negative charge of 10 volts, now back to 0. But this goes from tens, hundreds, and then thousands of volts. What I've got here are two panels. One is plastic, one is metal. And what I'm going to do is I'm just going to rub these together just like this. And you'll see it probably, I'll do it just off camera. But if I hold the plastic over the top, you can see there that I've got about 7,000 volts on there. If I move it around, it may go up 8,000 volts. I'm going to put that down on the work surface here. I have my metal one, and as I say, metal will charge up as well. I don't have as many volts on the metal one, but it's about 1,600 volts. And I'm going to put the metal one down on the work surface as well. Atmospheric voltage is now about 110 volts, just from where I've been moving around on the chair here. And if I pick this back up, the plastic, you can see that now that that's gone 1, it's actually over 20,000 volts there on just this piece of plastic. If I was to pick up the metal one, there's hardly any charge on there at all. There's a little bit of charge on there, but not much at all. There we go. So that charge from that metal surface will go away to ground. Now, if I was to have a plastic item inside my ESD protected area on my grounded work surface, so this is our blue work surface here. If I fold this up here, this is a conductive layer underneath, so our blue dissipative layer here. If I was to pick up, again, the plastic that's got over 10,000 volts on it, and pick up the metal that's got nothing on it now, and if I hold these quite close together, they're not going to touch, but I'm going to hold them quite close together. And what should happen is now there's a charge of 1,800 volts at peaked out there on the metal. There is still going to be a charge on the plastic. If I was to pick that metal up again, charge. Still a little bit there. Not much. It takes a little bit of time to dissipate away if I was to pick that up again. See there, no charge on the metal. Whereas with the plastic, that can induce a charge onto the metal surface. So anything that's plastic needs to be at least 30 centimeters or 12 inches away from sensitive products. At about 20,000 volts, I'd want that pretty much outside of my area. If this was a working area where I have boards, sensitive components, things that could get damaged by ESD events. So it's a nice, quick, easy demonstration there, just to show you the difference between the two materials. One that could be grounded, one which is a metal one that cannot be grounded, the plastic, and why we need to make sure that the plastic items are kept outside of the ESD protected area or are neutralized using an ionizer, which we will get onto a little bit later on. What I'll do is I'm just going to go back to the PowerPoint presentation so that you're able to see the next part that we're going to be talking about, which is kind of charge generation every day and different things that happen inside the ESD protected area. So I'll just stop my camera there for a moment and we'll get back on here. So here are some typical electrostatic voltages for everyday life. So there are many common activities that people perform on a day-to-day basis, okay? And these everyday movements, let's say, or activities, some are harmful, or all of them pretty much are harmful to electronic components. Now, the higher number that you're going to see here is generated at low humidity. But let's just say if someone's walking across a carpet, it could be up to 35,000 volts. It's not enough to kill someone. It will hurt. It'll make you jump, definitely. But as you saw, there, walking across carpet, that's very, very low humidity, as you can see on the screen. So that's not an everyday occurrence. But that's why we need to test, or companies need to test their items for product qualification before they're shipped out to the end user at 12% relative humidity to make sure they work. Walking over an untreated vinyl floors up to about 12,000 volts. There. A vinyl envelope, so these are the ones that you can get in supermarkets or different stationery stores, up to about 7,000 volts on there. All of these items, there are ESD versions of these. Now, working at a bench, up to about 6,000 volts, depending on their movements, what they're wearing, if they're wearing wrist strap, if they've got heel grounders on. Remember, if an operator is sat down at a workbench, they need to be connected to ground via a wrist strap. Okay, using ESD shoes or foot grounders isn't an acceptable way to ground someone through when sitting down inside an ESD protected area. And the reason for that, you can see it from the image here or the drawing here, that the operator that's working on the board, they have their wrist strap on, but their feet, one foot isn't firmly on the floor. Now, if both feet are on the floor, they're not grounded if they're not wearing a wristband. So wrist strap systems need to be used, or wrist straps need to be used when an operator is sat down at a workbench working on ESD sensitive devices. And unwinding regular tape, that's up to about 15,000 volts again, lower humidity. It could be more than that, depending on the area of the tape, how large the tape is. But just for normal sellotape, it's about 15,000 volts on there. So as I say, for working at a bench, you need to be grounded via a wristband. So what's important there is to make sure that the operators are grounded in the right way. And we will get onto that pretty soon. But it's important. As I said before, people discharge frequently, but to feel a discharge, the charge needs to be about 2,000 to 3,000 volts for us to feel it. And this is when you feel a shock. A lot of people say, "Oh, it's an electric shock. It's a static shock." Okay, so it's a static shock that you're feeling. And smaller charges below the threshold of human sensation, so below the 2000 volts, can damage ESD sensitive devices. Okay, so many components that are used in the facility can be damaged by discharges of less than 100 volts. Nowadays, now the components are getting more sophisticated, they're getting smaller, they're getting placed closer together. Because of this, it could be less than 100 volts that may damage a component. In some cases, it could be about 30 volts. Both IEC 61340-5-1 and ANSI ESD S20.20 work down to 100 volts. If you do have components that could be damaged by more than 30 volts, there are extra precautions you'll need to put in place. Things like having an ESD floor and still putting the items in static shielding bags, walking across the floor, maybe even using ionizers on the workbench, just to make sure that any charges that are there are neutralized. In terms of walking the product across the floor in a bag, it's making sure any charges that may be generated while walking stay on the outside of the bag before the bag is placed onto the work surface. So as I said before, ESD is a hidden enemy. So you need to consider that all electronic components are ESD sensitive. The ESD control plan may identify the classification of sensitivity to ESD damage. What that basically means is the ESD control plan needs to find out what the most sensitive device is. Once you find out what the most sensitive device is, treat all of the electronic components the same. Okay, going back to that first point there, the 2 points kind of intertwine with each other. And why that's important is we don't expect operators to know the difference between one component and another component, so what we want them to do is we want them to treat every single component exactly the same. It reduces operator error, it reduces extra training. So just treat everything. But if you do have a device that can be damaged by 30 volts, treat every single device as if it can be damaged by 30 volts, whether it can or not, if that's your most sensitive component. And as I say, new electronic components have a reduced width of circuits, they have a microscopic spacing of insulators, which increase their sensitivity to ESD. And if you remember back to the image before, ESD damage cannot be seen by the naked eye. We needed a magnification of 10,500 times to see the damage on the component before. But what we have here is an optical photo of a large integrated circuit board which has experienced some ESD damage to the pin. And that's where that orange arrow at the top of the image is pointing towards. Now, naked human eye, an image like this, you're not going to see that damage. So if we go in now and 400 times magnification, you can see the ESD damage there by that fuzz. But there are a couple of other bits of fuzz on there. It's an old photo, so it may not be that area. So we need to zoom in or magnify a little bit more. So 5,000 times magnification on the scanning electron micrograph, you can see the ESD damage there caused from that ESD event. If I put my arrow, here we go. So that there is the ESD event, or the ESD damage to the component after the ESD event. Now, what this could lead to, there are two different types of ESD device damage. We have catastrophic failures, which inspection is able to detect a failure, which is good in a way. It hasn't left the facility. There's testing in place, found an error with a component, and it's dead, and it will never function again. That can be replaced. The component can be removed, a new component put in place, item shipped out to the customer. That's the easiest type of ESD damage to find, as is detected during testing. It's what we want to find. Okay, we don't want customers getting any devices that could go wrong, and this is called a latent defect. So that component is wounded, but inspection passes as good. So there's an ESD event that's occurred, ESD damage has occurred, but it's not quite stopped the device from failing while it's in the facility. It goes out to a customer, okay, and that customer could be anyone. But this is what it does. So it passes all the different inspections. It works a while for a customer, and then it starts having problems and upsets, which then leads to more returns, more warranty costs, lower customer satisfaction, and more time for a team of rework team to rework a board because of one component that stopped working, and it could be because someone didn't wear wristbands that morning. So most of the time, the device damage that we're going to see is a latent defect. So if you can think about the electronic items that you've had just at home, maybe, and how things have worked for a while and then they've stopped. Maybe a backlight of a TV has stopped, or a phone has stopped working, or a microwave has stopped working. All of these could be because of latent defects and not having tight enough ESD control procedures and measures in place. And so what this could lead to, so this is a study that looks at the repair cost. The repair cost is not just the cost of getting a new component and reworking a new component. It could be the cost of losing a customer. It could be the cost of losing business while something else is being rectified. So if this £10 device went into a board, and say that board is £100, that £10 device in a board and a system, that's £1,000. And that £10 device in a whole system that fails, that £10,000, depending on what you're working on and who you're working with, could then cause further issues down the line. As I say, losing customers or more warranty costs, more time to have a look at the issues that's there, to see what device has failed, to test again to make sure everything's working. It just adds up. And what we need to do, and what we do at Desco Europe, is support customers to stop things like this from occurring. So, as I say, catastrophic failures. Catastrophic sounds terrible, but we like catastrophic failures, if any failures at all, because they're detected during inspection. Now, one case study said that for every one catastrophic failure, there's another 9 latent defects that have passed as good. So failures are very important to keep an eye on. See if the same products are coming back all the time, if it's the same component that's failing all the time, or different components are failing on the boards. It's going to help see where the problem lies. But if operators are testing and wearing personal grounding devices, whether that's a wrist strap, whether that's footwear, and they are testing them on a daily basis, it's easy to tick a tick sheet to say that you passed a test without actually testing. All of these things that maybe get into being bad habits, things that have been happening over time, then lead to latent defects. So as we say, latent defects, they are the most frustrating. They pass the inspection as good, they then fail later, and then it impacts customer satisfaction, costly field work, cause equipment downtime if everyone's looking at why something's gone wrong with 50 items on one batch, and other things aren't being made. So we'll say that the hidden enemy is ESD events, ESD damage, because it cannot be felt, cannot be seen, and it's not detected through the normal inspection procedures. And one thing that we can link this to is sterilization in medicine. So, as it says here, damage caused by undetectable events that could be understood by comparing ESD damage to medical contamination of the human body by viruses or bacteria. And although viruses and bacteria are invisible to the naked eye, they can cause severe damage even before you can detect their presence. So in hospital, the defense against the invisible threat is the extensive contamination control procedures, which includes a sterilization. So we're aware of these benefits and the benefits of sterilization and isolation in medicine. And it's developing the same attitude about ESD and sterilizing items against contamination. So if you're just thinking as an operator working on the shop floor, the hidden threat of electrostatic discharge or an ESD event should be of great concern to you, because that ESD damage can significantly reduce the company's profitability in a way. That may affect your profit sharing, company's ability to compete in the market, and obviously customers there as well from that one customer. It's a chain. So making sure that you're doing everything right. If something does go wrong further down the line after the items have left your facility, it's making sure that what you're doing, you've got to be able to control what you can control, and it's making sure that people do, as I say, time and time again, making sure people have wristbands on, have foot grounders on, and they've been tested, they're working. Making sure the map's been, the work surfaces have been tested, or the flooring's been tested and passing. So all of these things add up to make sure that the ESD control plan is good and the ESD control plan is working. So there's a few things that we need to do to make sure these items are working inside an ESD protected area or an EPA. We need to identify the ESD protected area with signs. Operators need to know, visitors need to know, office personnel need to know where the ESD protected area is, so they need to take the right precautions when entering. If the visitor's entering an ESD protected area, they need to be with someone. So someone needs to show them around, make sure they don't touch anything. And maybe even the same for office personnel as well, making sure that they're following the guidelines, sticking to walkways if you have them. But you need to identify that ESD protected area. You also need to identify ESD sensitive items and provide the ESD control training, which is what this video is for you. So we're going to be looking at the basics of ESD control. There's a few things that if we do these 4 things right, then we make sure that our ESD control plan is working. It's in a lot better position. We're going to go through these in a little bit of detail as we move through this PowerPoint. So we need ground conductors. Here's a foot grounder. Again, we'll be talking about these in more detail as we go through the next slides. We need to remove or neutralize insulators with ionizers. And we need to shield ESD sensitive devices or ESD sensitive items when stored or transported outside of the ESD protected area or the EPA. So we need ground conductors, which, if you remember back before, this includes people. So the wrist straps need to be snug on the skin, make sure they do make contact with the skin. They're clean. Operators have their own wristband and coil cord. The coil cord is also tested, and the coil cord is connected to ground. Okay. There's more and more I'm seeing now wireless or cordless wrist straps. They don't work. You need to have a cord connected to ground, somewhere for that charge to go away from the operator to ground. Cordless wrist straps, the charge just floats around in the air somewhere, not too sure where. It doesn't work. That charge is going to stay on the person. The operator needs to make sure that they have a coil cord and it's connected to ground. Foot grounders, Also needs to be used that grounding tab, which you can see there is under the foot. They're worn on both feet and the contact the ESD floor. Make sure that the conductive strip on the bottom of footwear, heel grounders, is connected to the floor. They're not worn upside down the other way or inside out. So why is it important to wear wristbands or wrist straps? What I'm going to do is I'm going to go back to the camera and I'm going to show you why it's important to wear wrist straps inside the ESD protected area. At the moment we're showing 22 volts here. Let's just change this. Hopefully we'll get this to 0. Or as close to 0 as possible. So I'm just going to ground this out and make sure, there we go, and that we are at pretty much 0 there. It is going to keep going up a couple of volts, but there we are, we're at 0. What I'm going to do is I'm going to, you're not going to see this on the camera, but I'm going to hold my hand over the top of the static field meter. I'll move this further forward. Put my hand over the top, and I'm just going to shuffle my feet on the floor here. I'm just going to have a quick look to see how many volts I generate. About 800 volts or so, over 1,000 there. But I'm generating a charge. Remember, anything under 100 volts could damage a component. So what you want to do is you want to make sure that what you have in place, foot grounders, wrist straps, make sure that the operators are grounded to less than 100 volts. So again, what I'm going to do, just move my feet, have a little look here to see it's about 600 volts it peaked out. Now what I'm going to do is I'm going to put on this wristband, this wrist strap, and I'm going to connect this coil cord to ground. And you should be able to see there the wrist strap's on. And I'm just going to do the same thing and just moving my feet back and forth on the floor. You can see there's no charge there. If I was to disconnect the wrist band from the coil cord like this and do the same, you can see the charge is there. I'll put the coil cord back onto the wristband, move my feet again. There's no charge. And that's why it's important to ground conductors, including people, because if the wristband has been tested, working, and that coil cord is connected to ground, then the operator is going to be grounded while they're working at a bench. Foot grounders work the same way. Again, impurities in the human body sweat layer, make sure that any charges from that person go to ground through the footwear, through the floor, and away to earth. Just like a wrist strap and a coil cord, just like these, the footwear will not work without a floor. So you need to have an ESD floor working in conjunction with foot grounders, just like a wrist strap here or the wristband will not work without the coil cord. So you need to make sure that you've got everything in place. Part of the ESD control plan, part of a qualified materials list to make sure that you're using all the right equipment inside the ESD protected area. So once our operators or personnel grounding devices are in place and our operators are grounded, we need to make sure that wrist straps, and they must work, so you can test the wrist strap on a daily basis, or use continuous monitors, which can be used. If you'd like some more information on that, you can reach out to us, or can provide future videos for testing wrist straps and continuous monitors. And foot grounders as well, these must work. So test the foot grounder on a daily basis to make sure that the operator is grounded through the foot grounder, and when they walk on the floor, they are grounded through the floor. There are other tests that need to be done, but this is the daily tests for personal grounding devices for a compliance verification plan, which in a future video we will go through. But what we will do is today we're just looking at the basic parts of ESD control, ESD basics. But for compliance verification plans, there are some other tests that need to be done. Now, it's very important that work surfaces are grounded. They are an integral part of any ESD protective or ESD protective area. And this is in areas where hand assembly occurs. And so it's necessary for the work surface to be properly grounded. A lot of work surfaces will be grounded with a yellow plug that goes into the protective earth here. As you can see, the 3-pin plug for us in the UK and Ireland, we've got the 3-pin plug there with the connection from the matting to ground. These plugs are yellow. They normally say earth bonding point plug on them. Please make sure they are not disconnected. I have been to facilities where these have been disconnected and someone's plugged in a radio or other operators have plugged in their phones. Just please make sure that this yellow plug is always connected. Have a visual check to make sure that's connected and the stud on the mat is also connected to make sure that any charge that's generated when an operator is working on a workbench, that charge goes away through the workbench to ground, which is why when we were doing the panel test earlier, I was able to show the metal panel didn't have any charge on there when we put it over the static field meter because all the charge had been taken away to ground through the matting. And just like work surface matting, conductive floor mats also need to be grounded with a common ground point. That could be the same grounding point that's used for the work benches. As it says on the image on the left, a ring terminal can be attached to the top of some of the earth bonding point plugs. And what this will do is it will allow you to connect more than one work surface or floor matting to that earth bonding point plug. So all of your power sockets are not taken up by yellow plugs, but there are different ones available. And one of the most important things, you can do everything else correctly, and then the matting isn't cleaned or the flooring isn't cleaned, or it is cleaned but using the wrong materials. So please make sure that work surfaces, flooring materials that are used by the company are kept clean using ESD safe cleaners. The reason why they need to be ESD safe, alcohol can destroy matting, work surface matting, and regular cleaners contain silicon. Silicon is an insulator, so as you saw with the plastic panel that I had earlier, that plastic panel kept a charge and it can be grounded through the work surface. As silicon is an insulator, the same thing is going to happen with that silicon. It's just the charge is just going to stay on the top of that work surface there. So as I've said a few times, and I just said it there as well, insulators cannot be grounded. So it's very important that if insulators, because insulators cannot be grounded, they need to be neutralized. And to neutralize them, we can neutralize these through ionization. And how the ionizer works is it floods the area with ions, positive and negative. And these protons and electrons, they're like magnets, so opposites attract. So the negative are going to attract the positive. The negative electrons are going to attract the positive protons, and the positive protons are going to attract the negative electrons. A visual of this could be if you get two magnets and if you put north and north together, the magnets repel. but if you put north and south together on the magnet, they attract to each other. It's the same thing that's happening here. The positive protons are attracting the negative electrons, and the negative electrons are attracting the positive protons. So as you can see on the image on the right-hand side, one little party trick that I think a lot of people have done before is rub a balloon on some clothing and then stick the balloon to the wall. And the reason why that balloon sticks to the wall is because of the static charge. What will happen over time is that balloon falls away from the wall, okay? And that's because the natural ions in the air will be attracted to the balloon, and it will eventually neutralize the charge, but it takes a long time to do. Okay, so if I've got the plastic panel and I left the plastic panel on the workbench, over time, that charge will neutralize. It's far too slow to neutralize inside an ESD protected area to just do it by air, which is why we need to use ionization. And because it's quickly, what this ionizer does, it creates billions of ions, and they employ a high voltage to produce a balanced mix of positively and negatively charged ions. So it needs to be balanced, okay? Otherwise, the ionizer will be doing the exact opposite of what we want it to do. The ionizer will actually charge up the item instead of neutralizing the charge. It will either charge up positively or negatively. What an operator needs to do is they need to point the fans to cover the whole work area. And the ionization will reduce static charges on an insulator or isolated conductor. Okay, and there are different types of ionizers available. Benchtop ionizers, hand gun or air nozzle ionizers, overhead ionizers, and all of these will neutralize charges on insulators and isolated conductors. It's important that ionizers are cleaned periodically from the emitter pins to make sure they are not charging up, as I said just a moment ago. If ionizers work with the emitter pins, they've got an equal amount of emitter pins, the DC ionizers that we've got here do. And what these emitter pins will do is they will fire out the same amount of positive and negative ions, positive protons, negative electrons. If one of the emitter pins is damaged or dirty and is not sending out as many positive or negative ions, if it's sending out fewer negative ions, the item is going to charge up positively. Okay, so cleaning needs to be done periodically. Visual checks of ionizers also need to be done periodically because we want to make sure they are neutralizing the charge on the items on the workbench. And so where we're going to look at ionizers now is what I'm going to do is I'm going to connect an ionizer to power up the back of the workbench here. And I'm going to charge up my two panels again. And what you're going to be able to see is the charge neutralize on the on the plastic panel. So what I'm going to do is I'm going to go onto the camera. And I'll turn on my ionizer as well. So if I just move these out of the way for a second, I'm bringing this into shot. This is my ionizer here. You may not be able to see it, but we'll give it a go. Can just about, but just underneath the grill here, you can see two little pins. These two pins here 2 of the 8 emitter pins on this ionizer. There are 2 bottom, 2 top, and then left and right there are 2 there as well. And what that's going to do is that's going to be sending out the positive protons and the negative electrons. As this ionizer just self-balances, the light on the front is green, telling me that this ionizer is okay and it's working, it's all turned on. So the fan is spinning. You can probably hear that fan spinning inside the units there. And what I'm going to do, just leave that to the side of the camera at the moment, and I'm going to bring back in the static field meter here. And I'm going to charge up my plastic panel. And I'm going to place the plastic panel in the airflow of the ionizer. So remember that airflow is important. So I don't want that ionizer pointing up at the sky. I don't want it away from the product. I want it looking directly at the product to neutralize the charge. Now, if I was to pick this panel back up and hold it over the top, see there's next to no charge on there now. Again, if I was to do the same, so again, I'm just moving or rubbing the panels together. Placing the panel over the top, it's got about 2,000 volts on it. Hold it in the airflow of the ionizer, and then back over the top of the field meter, and that charge is neutralized. So using ionizers is important to neutralize any charge, as long as it's in balance on any insulators inside the ESD protected area working on that workbench. So a quick little demo there of how ionizers work, how those charges can be neutralized on plastics. And so we've had a look at the grounding of the conductors. We've had a look at ionization and making sure work surfaces are grounded as well. So what we're going to look now are bags or packaging. And what we need to do is we need to make sure that ESD packaging is used the right or the correct packaging is used inside the ESD protected area. So we've got this is what we like to call our third basic principle of ESD control, and making sure that the right packaging items are being used inside the ESD protected area. Now, when I say use the right packaging, what you'll see here, we've got closed metallized shielding bags mentioned at the top there. But we want to make sure that the bags that we're using are shielding to protect any ESD sensitive devices. We also want to make sure that any boxes that we're using acts as a Faraday cage. That Faraday cage makes sure that there's charges on the outside of the product and no charges going through the bag and damaging the components of the product inside. So the Faraday cage is the bag working around keeping the charge on the outside of that bag, not letting any charge penetrate the bag. So there's a quick little demo that we can show you here for using the right packaging. And what I will do is go back to the camera so you're able to see this in a second. And we changed our units, and this unit here is called an EMI ESD event meter. It's not an item that's going to check static voltage, just there. What it will do is it will pick ESD events. So what I've done here is I've charged up one panel with the plastic panel here, and I can introduce another metal panel. So I've got two metal panels here, and if I just knock them together, you can see there's an ESD event there that occurs because there's two metals of different polarities, and what that's going to do is it's going to cause an ESD event inside the ESD protected area. What this could be, this is our component, our conductive component, and this one here is an ungrounded person or operator. They're not using their wristband, they're not using footwear. They go to touch a conductive product or a board, and that charge goes from that operator onto the board, damaging the component, causing an ESD event. As I say, this unit here will not test for static field. What it will do is it will test for ESD events. So if I was to zero this back out, I have one type of bag that's normally seen inside of an ESD protected area, and that's a pink bag here. What I'm going to do is place the EMI meter inside this pink bag, and if I can lean it up, that'd be great. Okay, so you can just about see that says 0. Here I have a 0-volt stack gun, and what I'm going to do is I'm going to fire this 0-volt stack gun that creates a spark on the inside. So I don't want to touch the end bit here, but it creates a spark, and what that spark's going to do is it's going to go, and we're going to see if it goes into the bag and damages the components inside. Now remember from the PowerPoint we said that the bags need to be closed. They can either be closed or folded over. So what I'm going to do is I'm just going to fold this bag over, and I'm going to hold it here so that you're able to see. And if I fire the 0-volt stack gun, you can see that there are some ESD events there. You may even hear the beeping of the unit to let me know that, well, there have been 8 ESD events here, and I've been holding the bag. So the pink bags are good for bringing in items into the ESD protected area that are non-ESD sensitive devices, so things like screws, nuts, bolts, things like that, that may be needed inside the ESD protected area, but they're not going to be good for ESD sensitive devices. So ESD sensitive devices, they need to have a separate bag. And as I said before, closed shielding bags are the best bags for this. So just here I've got one of my metallized shielding bags. It's been beaten up a little bit, which is why we use this bag for this test. It's because some bags can be used over and over again, or some bags are used over and over again. And this is a good test to see if that bag can be used, if it's going to keep any charges outside of that bag. So if I was just to stand this up here, you can just about see that that says 0 on it. If I was to fire the gun, and you can probably hear that gun clicking. So again, just a 0-volt stack gun. There's no charge that's going through this bag into the ESD event meter inside, or the EMI meter inside. What that's doing is any charge is sent on the outside of the bag, and when I place that bag onto a grounded work surface, that charge goes away to ground. So what's really important if you're using bags is to make sure that you take any sensitive devices outside of the bag at a grounded work surface, okay, or at a grounded workstation. So what I'm going to do is I'm just going to go back to the PowerPoint for the last couple of slides. And there's a little bit of a recap now of everything that we've just gone over. And again, I will share my contact information so that if you do have any questions, please feel free to ask me. So just a reminder, this is what the standard says about packaging. But ESD bags should be closed and containers have lids in place. And ESD packaging only be opened at an ESD protected workstation by properly grounded personnel. And as I say, the reason why we do that charge stays on the outside of the bag. As soon as that bag is placed down onto a work surface, that charge dissipates away through that work surface, goes through the work surface and away to ground. So the things that we need to do, just as a quick recap now, ESD protected workstations are areas that have been established for controlling electrostatic charges and discharges. Things that we need to do at these workstations are grounding all conductors, removing all insulators, or at least keep them at least 30 centimeters apart, or neutralizing process essential insulators with an ionizer. We can also remove insulators or change them to ESD protected versions. And here's a few ESD protected versions that are available. As I say, there's tape, flooring, the ring binders, and document holders. If you remember back to the child generation of people walking across carpets, walking across vinyl tiles, and the normal vinyl envelopes, all of these charge up and can hold a charge. They are insulators, so change these to ESD protected versions. You need to make sure that as you're on the front line fighting the hidden enemy, remember ESD control damage or ESD events, only allow trained or escorted people inside the ESD protected area. So if you have visitors, office personnel that maybe haven't been trained in the ESD basics, but escort them around the premises. Grounding all conductors, so people at these ESD workstations. Test the wrist straps and footwear at least once a day. You can use continuous monitors for wrist straps. If you use continuous monitors for the wrist straps, you do not need to do daily testing. Footwear, there are no continuous monitors for footwear at the moment, so they need to be tested at least once a day. For operators at their workstations, visually check that all the grounding cords are connected. The bonding point plug is connected at the back of the workbench. Handle unpacked ESD sensitive items only when the operator is grounded, the work surface is grounded. Make sure that wristband is snug and the foot grounding tab is in the shoe. And if smocks are used or lab coats, make sure those smocks are buttoned up. The reason why the smocks need to be buttoned up is similar to packaging. The packaging acts as a Faraday cage to protect what's on the inside of the bag from the outside. The smocks are flipped. So what they're doing is they're protecting the items on the outside from the clothing on the inside of the smock. Clothing, a lot of clothing is insulative. It's going to charge up, it's going to hold a charge, and then it's going to discharge onto products if it's within 30 centimeters or 12 inches of sensitive devices. And finally, we need to make sure that ionizers are maintained and the airflow is directed at the ESD sensitive devices, not at an operator's face or away from product or turned off, because an operator's hands are cold. They need to make sure that they are on and directed at the sensitive devices. And the regular checks or periodic checks are carried out to make sure the emitter pins are clean and that they're not going to be charging up the product either positively or negatively, depending on how out of balance the ionizer is. And then you can use discharge shielding packaging for shipping or storing ESD sensitive devices outside of the ESD protected area. So that using the metal shielding bags or tote boxes or boxes that have got shielding properties to make sure that the items inside cannot be damaged by any ESD events or suffer any ESD damage. But that's it. Thank you for your time. If you'd like to contact me, my email address is tim.hacker@desco.com. That will be in the comments of the video. Along with my mobile number. If you do have any questions or if you'd like to talk about anything in more detail, please let me know. But thank you for your time. And if there's anything we can support with, please don't hesitate to contact us. So thanks again for your time and take care.